All right, we have a little bit of notes from 7.1 that we didn't get to yesterday. There's models or equations for exponential growth and for exponential decay listed right here at the top. The A means the initial amount, R is your rate, you're going to change it to a decimal if it's a percent, and your T is time. So we're going to go through a couple of examples. The initial number of bacteria in a culture is 12,000. The culture doubles each day. So write an exponential function to model the population y of bacteria after x days. So the fact that it doubles each day tells us it's growing rather than decaying. So this is going to be an exponential growth model. So a of t is equal to the initial amount. We know the initial amount, 12,000, times 1 plus, now rate. Now they didn't tell us the rate as a decimal, but it doubles each day, so it grows by 100%. So 100% as a decimal is 1.00. To the exponent of t, we're talking about x days. We're measuring in days rather than years, but I would put that as an x. I could simplify that slightly, because in the parentheses, I can write that as 2. I guess technically, since we used x, they told us to use an x in the parentheses here. Instead of a sub t, I should write a sub x. And they also told us, I guess, to write y. So I don't even need to use the function notation. This isn't that big of a deal. If you would have used it, that's fine. But they told us just to use y. So y equals 12,000 times 2 to the x. And so part B now, how many bacteria are there after 6 days? So now we take the equation, we plug 6 in there. So we're going to take 12,000 times 2 to the 6th power. Type that in the calculator. 12,000 times 2 to the 6th power. And I get 768,000 bacteria. Okay, next, a college with a graduating class of 4,000 predicts that its graduating class will grow. So this is growth. Again, we don't have an example on here of decay, but if it was decay, we use the exact same thing, but use a minus. But this one is growing 5% per year. Write an exponential function to model the number of students y in the graduating class t years after 2008. So you're saying to use y and t for the variables. Sorry, my pencil's running out of lead. Okay, I'm just switching to a pen, sorry. So growth, so y equals initial amount. They tell us 4,000 students initially. 1 plus. Now 5%, we have to change that to a decimal. So you move the decimal, it's after the 5 right now, but you move it 2 to the left. So we have to put a 0 in there, so it's 0.05. Close the parentheses. To the exponent of t. And there we go. It doesn't ask us to predict the number of students in any year, so we're just writing the equation. If they asked for like 2012, that would be 4 years after 2008. You'd plug a 4 in for t, and you could then evaluate. Okay, now 7.2. There's this rule that if b to the x equals b to the y, we know that the exponents have to equal each other. X has to equal y. So we want to get, in these equations we're going to do 1 through 4, we want the base numbers to be the same so that we can drop the base numbers. So in number 1 we have that 2 to this power equals 2 to that power. So the two powers, 2x and 4, must equal each other. So we can write that down and then solve that. So I would divide by 2, and I get x equals 2 as the answer to the problem. But now when I look at number 2, they don't have the same base numbers, 2 and 4. But 2 and 4 can both be written as powers of the same thing. They can both be written as powers of 2. So I'm going to leave the first one as is. The 4 I can write as 2 squared. Very important to notice, I did not change the value. I didn't change the 2 to a 4 because that's different. I just changed 4 to 2 squared. It's the same thing. I didn't change the value, but now I wrote it as a base of 2. Now I have an exponent, and it's raised to an exponent, so you have to multiply those exponents. So distribute 2x plus 2. Now we have the same base number, so now set the exponents equal to each other. 4x equals 2x plus 2. You're going to subtract 2x. I didn't give myself a lot of room here. So 2x equals 2, so x would have to equal 1. Number 3, 4 and 64 can both be written as powers of 4, or of 2, but 4 is easier, because the first one already is a 4, so we can leave the first one alone. 64 is 4 to the third power. I didn't change the value, but I wrote it as a base number 4. Now I have the same base number, so my exponents have to equal each other. 2n minus 1 has to equal 3. Add the 1, 2n equals 4, so n has to equal 2. Number 4, a little tricky. We have a 9 that's in the denominator, and we have a 27. Those are both powers of 3. 9 is 3 squared, but it's in the denominator, so to bring it up, we have to make the exponent negative. So 1/9 is the same as 3 to the negative second. 27 is 3 to the third. Okay, distribute multiply your exponents. So negative 4x. Distribute here, so negative 3x minus 9. Now set the exponents equal to each other. Negative 4x equals negative 3x minus 9. I would add the 4x over. So then as you're doing that, we're going to add the 9. So on this side I just get 9. And then on this side I get x. So x equals 9. Now we have a new model or new equation for compound interest. So if you go to a bank and you get interest and they say it's compounded monthly or daily or weekly, that type of thing, we would use this model. The n is a lot of the same letters as before. P stands for principal, that's the initial amount. N is the number of times it's compounded in a year. So let's take a look at this example. 4.2% interest, compounded monthly. So monthly, so the n is how many times that is, how many of those there are in a year. So if it's monthly, that's 12 times a year. So we're going to use an n value of 12 for that. So let's write our equation. Our initial amount, our principal, $2,500 is what was deposited. 1 plus your rate, we have to change it to decimal, move it 2 places to the left, 0.042, and that's divided by 12. And then your exponent, 12 times the number of years, we're looking at 15 years. Be careful in calculators, depending on what calculator you use. If you probably either need to multiply 12 times 15 ahead of time so you know what the exponent is, or put parentheses around it. So, for example, actually, I'm going to use a scientific calculator instead of the graphing calculator. The graphing one doesn't need the parentheses. This one we probably do. 2,500 parentheses 1 plus 0.042 divided by the 12, close the parentheses, raised to the exponent of, and now I need parentheses around 12 times 15 so the calculator understands that both the 12 and the 15 are in the exponent. Hit enter, we get our answer, $4,688.87. And then, next one, find the account balance after 20 years. If $100 is placed in an account at 1.2% interest compounded quarterly. So quarterly, there are 4 quarters in a year, so we will use an n value of 4 on this one. The initial amount was $100. 1.2% interest, 0.012, compounded quarterly, so divided by 4. Your exponent is going to be 4 times, and we're looking at 20 years. So we're going to go 100, 1 plus 0.012 divided by 4, close the parentheses, to the exponent of, and this time I might just type in 80 instead of using parentheses, because I know 4 times 20 is 80. I get $127.08. Didn't make much money in those 20 years. All right, so that's the end of the notes. Now, if you look at the back side of this, this is going to be your assignment. There's some word problems, and then there's some solving equations. This is going to be due in class, so you'll do it now. You'll turn it in. I will make sure to get it back to you. I won't keep this worksheet after you turn it in because I know you've got your notes here, so I want you to get it back. But you will turn it in. I'll check it and get it back to you. But that's the end of the notes for today.